so back with the next set of questions. Question number 6. Particle is initially at rest at the top of a curved frictionless track. X and Y coordinates of the track are related in dimensionless units of y over x squared, or y equals x squared over 4, where the positive x is in the vertical downward direction as the particle slides down the track. What is the tangential acceleration? All right, so let's do a little doodle. So I've got that. Boom, let's pretend that is a flat axis. All right, so if I want the tangential, that's going to be the derivative. So I get that's the tangential acceleration. I've got boom. That's my change in y. That's my change in x. Call that theta. So from this we can get that the tangential acceleration is going to be, let's just make sure, g cos of theta. Also, y is x squared over 4. If I want that, we'll just get the derivative as well, x over 2. All right, now let's pull this triangle out. Boom, boom, boom. There's my theta. There's my dy, dx. Tangent of theta is equal to dx dy. We'll pretend that's a y. So going from there, I can just imagine that as 1 over dy dx. So I can flip that, meaning tangent of theta is the inverse of the derivative, which just gives me 2 over x. Now I'm going to draw another triangle. This question really likes the triangles. This is basically a shape question. So I have there, I'm going to have x2. That's also theta again. From there, we're going to have x squared plus 4 as the long arm. So we're kind of almost done with this question. Almost seems like you're going in circles or not really going anywhere, but we're pretty much done. So now I take ATG cosine, and what is cosine of that? It's going to be, wait, I'm sorry, that should be that way. That should be x, that should be 2. So now I get x over root x squared plus 4. And then just going to plug that back into A. And we get gx square root x squared plus 4, which we go over. Would you look at that? Right there. All right. Next question. There's a lot of writing. Next question. A 2-kilogram box hangs by a massless rope from a ceiling. A force slowly pulls the box horizontally to the side until the horizontal force is 10 newtons. The box is in equilibrium as shown above. The angle that the rope makes is closest to. Alrighty. So let's draw our little diagram. I always like to redraw everything just so I think through it as I draw. So 2 kg. I'm going to do a little force diagram on that. So we've got that's theta. I want to extend this, and also that's theta. So from there, I'm going to do a little more triangle-y stuff. I'm going to have, since they said it's an equilibrium, I know that the F pull, which I'm just going to call the component for that, is going to be F cosine of theta, and the gravity component is is going to be, what the hell? Is going to be mg sine of theta. So again, by combining those two things, I can set them equal, and then basically you just kind of plug and chug and solve. So I have mg sine theta is equal to f cos of theta, and I'm going to tack that up here. So just doing some of the math behind the scenes, mg over f is equal to cos over sine. But it looks like it's sines and tangents, so I could flip this and flip that, and that's going to give me f mg equals tangent of theta. So this is starting to look right. Plugging in these numbers, you have 10 and 2 times 10 equals tangent theta. Boom, boom. So you have a half tangent theta. Therefore, theta equals arctan of a half, which is right there. So it looks like that one worked out pretty well. Next question. All right. There we go. So a lot of these questions, it's not my favorite test because it often boils down to how many equations do you know and how many weird forms of the equations do you know. So I see this one and I'm given a mass, 5 kilograms, a delta x as the nail gets pushed down, a v, and I'm looking for a force. Force and delta x should make you think of work. With a v and an m, you should also think kinetic energy, 1/2 mv squared. This also helps. So the work is equal to force times the distance. Is also equal to the change in the kinetic energy. So I'm just going to rewrite this down here. Actually, no, not just that. There we go. So I can just write that second part, and you can see if I solve for F, I have F is equal to change in kinetic energy over a change in distance. So how much, I don't know why I wrote that many x's, there we go. How much does the kinetic energy change over a certain given distance? Now essentially I just set this up. So I have the force is equal to 1/2 mv final squared minus 1/2 mv initial squared over x final minus x initial. I'll do that over here. The final velocity is going to be 0 because the brick or the stone is falling and then stopping. The initial velocity is that 10 meters per second. The x final is minus 0.25 because it starts at 0 and gets depressed by that much. So that's how you want to think of that. So given those things, that's going to cancel out, and then that's going to cancel out. So I'm left with minus 1 mvi squared over x final, which is going to be equal to, I don't have room there, just make it all happen on this line, 1/2 minus 1/2 5 kilograms, and then 10 meters per second squared, and minus 0.025. So the minuses cancel, and that becomes 250 over 0.025, which is 10,000 newtons, which is not answer E. Answer D. Alrighty. Let's see. Oh yeah, this is a question where do you know the equation? If you don't know this equation, good luck. So you have a wire with a diameter of 0.02 meters. Number of electrons, hash, n is equal to, I'm just going to write 10 to the 28. Electric current of 100 amps. Find the drift velocity. So the equation for drift velocity is current over number of particles times the area times the charge of the particle. So is it 6-ish, 10 to the minus 19 coulombs. So plugging things into this equation, it wants us to get what's the closest, and looking at the powers of 10, they're all quite far apart. So I'm just going to kind of just focus on the powers. So current, it's 10 to the 2. Then the number, that's 10 to the 28. Then the area, that's going to be 10 to the minus 2 squared, since I'm going with area. Charge is 10 to the minus 19. If I have, combining all the things on the bottom, I have 1028, 1019. That leaves us with 10 to the 9. 2 gives us minus 4, so I'm going to end up with 10 squared over 10 to the 5, which is going to give 10 to the minus 3. Looking at the answers, this is the closest. You can kind of argue that things like this, the pi that would go in with the area, those would give a little bit of a kick, so you end up with close to D. So we'll pick D. But just a little bit of a dimensional analysis, not necessarily dimensional analysis, but just working with exponents and powers and simplifying the problem. But again, if you don't know the equation, good luck. Question 10. Given a little graph, an isolated sphere of radius r contains a uniform volume distribution of positive charge. Which of the curves on the graph above correctly illustrates the dependence? Cool, I just did my pencil. There it is. Which of the following curves on the graph above correctly illustrates the dependence of the magnitude of the electric field of the sphere as a function of the distance radius from its center? If you know this, you know this. If not, you don't. So if I have a sphere, radius r, the graph of the electric field goes up until you hit the radius, and then it flattens out, so it decays. So looking at those, the answer is C. If you know it, you know it. If you know Gauss's law, you can kind of set up and get an idea for it. So I have that. Setting this up, you have E, then the surface area of the sphere. And then this, since it's a uniform charge, it's going to be just 1. Just keep it as a density of 1. That's just going to give you the volume of the sphere then. Just doing some cancellation. The 4, not the 3. The 4 and the pi cancel out. That goes away. That goes away. And I have that the electric field is R over 3 epsilon naught, which is linear, which again only matches C as the increase. So again, you kind of get the answer C. 2 different routes, but again, that's one of those questions where if you know it, and it's significantly easier.